Okay guys, today I will explain about phase equilibrium in the simple system, the phase rule. The material, the phase diagram, the problem of component, the integration of the clapeyron equation, effect of pressure on the vapor pressure, the phase rule. The first material, the phase diagram. The phase diagram shows at a glance the properties of substance: melting point, boiling point, transition point, triple point. Every point to phase diagram represents a state of system. Since it describes value of T and V. The line on the phase diagram divides it into region labeled solid, liquid, and gas. If the point describes the system falls in the solid region, the substance exists as a solid. If the point falls in the liquid region, the substance exists as a liquid. If the point falls on a line such as the substance exists as liquid and the vapor in equilibrium. The 1 minus G Jarvie has a definite upper limit at the critical pressure and the temperature sign. It is not possible to distinguish between liquid and gas above this pressure and the temperature. Next, the phase diagram for carbon dioxide. The phase diagram, look at this diagram. The phase diagram for carbon dioxide is shown schematically. The solid liquid line slopes slightly to the right side. V liquid is greater than V solid. Not that liquid carbon dioxide is not stable at the pressure below 5 atm. For this reason, dry ice is there under ordinary atmospheric pressure. When carbon dioxide is confined to a cylinder under pressure at 25 Celsius, the diagram shows that if the pressure reaches 67 atm, liquid carbon dioxide will from chemical cylinder of carbon dioxide so commonly contain liquid and gases in the equilibrium. The pressure in the cylinder is about 67 atm and 25 Celsius. The phase diagram for water is the phase diagram for water under moderate pressure. The solid liquid line slightly to the left because V liquid is less than V solid. The triple point is at 0 times 0.1 Celsius and the 61 VR. The normal freezing point of water is 0 times 0.002 Celsius, and increase its pressure decreases the melting point of water. This lower melting point under the pressure exerted by the weight of the scattered through the kinetic edge of the skate blade is part of the region that is skating is possible. This effect, together with the heat developed by friction, combined to produce a lubricating layer of liquid water between the edge and the blade is disconnected. It is interesting to note that if the temperature is low, the skating is not good. Next, the phase diagram for sulfur. So to phase diagram for sulfur, the stable form of sulfur at ordinary temperature and under 1 atm ratio is rhombic sulfur, which if had slowly transformed to solid monoclinic sulfur at 95 times per Celsius, above 95 times per Celsius, monoclinic sulfur is stable until 119 Celsius is raised. Monoclinic sulfur melts at 190 19 Celsius. Liquid sulfur is stable up to boiling point in 444. The transformation of one crystalline commodification to another is often very slow, and if rhombic sulfur is heated quickly to 114 Celsius, 140 Celsius is melt. The melting point of rhombic sulfur is shown so as a function of pressure in the equilibrium as rhombic S1 is an example of a much stable equilibrium since the length is the region of stable of monoclinic sulfur. Second material, the integration of the clapeyron equation, solid-liquid equilibrium. The clapeyron equation dV per divide dt equal delta S push divide delta V push. Then the integral V2 V1 dV equal Tm integral Tm delta H push divide delta V push dt per T. If a delta H push and delta V push are nearly independent of the T and V, integrates to V2 minus V1 equal delta H push divide delta V push ln Tm divide Tm, where Tm is the melting point under V2 equal Tm is melting point under V1, since Tm minus Tm is usually quite small. The logarithm can be expanded to ln Tm per T divide Tm equal ln Tm plus Tm minus Tm divide Tm ln equal ln 1 plus Tm min Tm divide Tm. Then delta V equal the delta H push divide delta V push delta T divide Tm, where delta T is increasing. Delta T is increasing in melting point corresponding to increase is pressure delta V. Next, condensed phase gas equilibrium. For the equilibrium of a condensed phase, either solid or liquid, with vapor, we have dV divide dt equal delta S divide delta V equal delta H divide T Vg minus Vc, where delta H
is either the molar height of vaporization of the liquid or the molar height of sublimation of the solid, and Vc is the molar volume of the solid or liquid. Learn more circumstance Vg minus Vc, and this assuming that the gas is ideal is equal to RT divided V, then the equation becomes d ln V divided dt equal delta H divided RT quadrat, which is the Clausius-Clapeyron equation, relating the vapor pressure of the liquid to the head of vaporization, sublimation, and the temperature integrals between limits. Under the addition assumption, the delta H is independent of the temperature yield. Integral V d ln V equals integral T delta H divided RT quadrat point dt. V divided V0 equal minus delta H divided R, or 1 divided T minus 1 divided T0 equal minus delta H divided RT plus delta H divided RT0, where V0 is the vapor pressure at 0 and the V is the vapor pressure at T. If V0 equals 1 atm, then T0 is the normal boiling point of the liquid or normal sublimation point of the solids. The third material effect of pressure on the vapor pressure. If by some means it is possible to keep the liquid under a pressure V and the vapor under the vapor pressure V, then the vapor pressure dependent on V. Let the space above the liquid the vapor is confined together with a foreign gas that is insoluble in the liquid. The vapor pressure V plus the pressure of the foreign gas is V. The total pressure exerted on the liquid, as usual, the equilibrium condition is V5 or T point V equal V liquid or T point V. At constant temperature, this equation implies that V equal F or V. To discover the functionality is differential with respect to V, keep T constant. dV 5 divide dV point T, dV divide dV point T equal dV liquid divide dVT, using the fundamental equation V5 or dV divide dV point T equal V liquid or dV divide dV point T equal V liquid divide V vapor. So that the vapor pressure increases with the total pressure on the liquid. The rate of increases is very small since V liquid is very much less than V vapor pressure. If the vapor we have ideality, RT divide V times dV equal V liquid times dV. RT integral V divide times dV divide V equal V liquid integral V times dV, where V where V is the vapor pressure under a pressure V. V0 is the vapor pressure when liquid vapor are under the same pressure V0, the atmospheric pressure. RT length V divide VO equal V liquid or V minus VO. We will use the four material the phase rule. The coexistence of the phase in the equilibrium implies the condition VA or T point V equal VB T point V, which means that the two intensive variable ordinarily needed to describe the state of a system are longer independent, but are related because of the relation on the intensive variable, either temperature or pressure, is needed to describe the state of the system. The system has one degree of freedom or is univariant, whereas if only one phase is present. Two variables are needed to describe the state, and the system has two degrees of freedom or is bivariant. If three phases are present, two relation exists between T and V. VA T point V equal VB T point V. VA T point V equal VY T point V. These two relations determine T and V completely. No another information is necessary for the description of the state of the system. Such a system is invariant, has no degrees of freedom. The table suggests a rule relating the number of degrees of freedom V to number of phases V present F equal 3 minus V, which is the phase rule for a one component system. It would be helpful to have simple rule by which we can decide how many independent variables are required for the description of the system, particularly in the study of systems in which my component and many phases are present. A simple simplification of the problem is welcome. We begin by finding the total conceivable number of intensive variables that would be needed to describe the state of the system container C component and the V phases.
Okay, the last material, the problem of component. The number of components in a system is defined as the last number of chemical independent species that is required to describe the composition of every phase in the system. A fact value, the definition seems simple enough, and in ordinary practice it is simple. A number of example will be shown of the joker in the deck to little phrase chemical independent. Example: the system contains the species VCl5, VCl3, Cl2. There are three species present but only two components because that equilibrium VCl product VCl3 plus Cl2. lactam is established in this system. One can alter the number of moles of any two of these chemical individuals arbitrarily. The alteration in the number of moles of the third species in the fixed by the equilibrium condition K equal X VCl3 HCl2 divide HVCl5. Consequently, on any two of these species are chemically independent. The third is not. There are only two components.
What you're given, that's how we live it. Don't be mad at the system, it's simply how we've existed.